Greetings Internet, Sean Shipping here and welcome to my lab. In a previous experiment I showed how to deploy an OpenStack cloud using Juju and Metal as a service, but a lot has changed since I published that. OpenStack has had a couple of new releases, so have Metal as a service and Juju, but most notably the deployment method I used the last time has changed quite drastically. I used to use the Juju GUI pretty extensively, but since then it's been deprecated and replaced with the Jazz dashboard. So in today's experiment, not only am I going to be deploying OpenStack using the Juju CLI exclusively, I'm going to be deploying everything without a single point of failure. In this experiment, I'm going to be deploying a modified version of the OpenStack bundle found in the Juju Charm store. The bundle includes all the basic services needed for a functional OpenStack cloud. This includes compute, network, storage, an identity provider, image repository, and OpenStack dashboard. The bundle doesn't take any high availability considerations into account, so I'm going to be adding and modifying a couple of components to end up with something a little bit more robust. So whether you decide to deploy the standard bundle or completely over-engineer your HomeLab like I have, the requirements for the bundle are as follows. We will need a MaaS region controller, a Juju controller, at least 3 physical servers with a minimum of 8 gigs of memory, 2 physical disks, and 2 cabled network interfaces. Obviously, we'll also need a network switch, preferably 2 if you're going to do high availability networking, and a router or firewall which provides access to the public internet. A little bit about how the hardware gets utilized. The first hard drive in each physical machine will be used for the node operating system and any ALXC containers that we decide to make use of. Storage, compute, and some networking components are installed directly onto the node OS. All other services are containerized as LXC containers, which is a great way to isolate services from each other, but it also condenses the deployment footprint. The second hard drive is for Ceph distributed storage, and this is where our OS images, virtual machine disks, and object storage will get written to. And then a little bit about how the network is utilized. Traditionally, the first network interface is for communication between cloud services, also referred to as east-west traffic. The second interface is used for north-south traffic, which is communication between resources inside of the cloud and external networks. Now, as mentioned, I'm going to be deploying a modified version of this because I don't want any single points of failure. So I'm actually going to be deploying 6 physical servers, deploying all the OpenStack services in triplicate, and then horizontally clustering that across all of the hardware. I'm also going to be configuring the network interfaces in an active backup bond, and then use VLANs to separate east-west and north-south connectivity. By doing it this way, if any of the servers or switches fail, neither network or OpenStack service availability is impacted. So I already have a MaaS and Juju controller, so technically I'm kind of at the point where I can already enroll physical machines into MaaS and begin deploying OpenStack to them. But before I do that, I do want to talk a little bit about the networking so that it makes a little bit more sense. In MaaS, I've configured multiple VLANs and subnets and associated them with different spaces. Spaces are just a logical construct which MaaS and Juju use to place servers or applications in different network segments. If we want, we can define spaces and use them for different things. So for example, when OpenStack services speak to each other, we may want them to do that across internal private network. When administrators perform admin tasks on the platform, we can make that happen over an admin network. Or if we want to allow external clients to be able to interact with OpenStack APIs, we could tie those APIs to a public network. Now, for this experiment, I'm only going to be using the Pixie and admin spaces, but it should be enough to clarify how MaaS and Juju configure the network on deployed nodes. In order for us to deploy machines using MaaS, each bare metal node is configured to use the network as its first boot device. But when a machine boots, it's reasonably unintelligent, so it doesn't even know what a VLAN is. Any network packets that it sends or receives will be classified as untagged traffic. Therefore, it will automatically be dropped into this subnet and in turn be associated with the Pixie space. Now, ideally, I don't want my deployed servers to be tied to my provisioning network. So what I'll need to do is I'll need to configure the interface or VLAN and assign it to the relevant space before deploying an operating system to it. Now, obviously, if you're going to be using VLANs, you're going to need managed network switches. In this experiment, I'm not going to be covering any of the network configuration, but I'm going to be concentrating mainly on the MaaS and Juju side of things. So when a node boots, it gets a PXE address from MaaS and undergoes either a commissioning process or a deployment process. Machines MaaS has never seen before will eventually turn up in the MaaS GUI with a state of new. So over here, I have 3 machines, one of which is new because it's literally just been installed into the rack. And the other 2 are machines that I've already started to configure. Before machines are usable, they need to be in a ready state. And to get machines to the ready state, I need to formally commission it. MaaS will turn on the machine using the IPMI information it learned during its initial commissioning, and it will PXE boot again, and MaaS will then poke sticks at it and learn as much as it can about the capabilities of the machine. After that, it'll be in the ready state, and I'll be able to configure the desired target state of the machine. So while this one goes through its formal commissioning, let's configure the networking on a machine that's not quite ready. Now, as mentioned, I want to configure bonded networking to avoid any outages caused by switch or link failures. So I'll go to the network on a machine and create a bond from the 2 interfaces that I have. The bond mode is active backup. I'll call it bond 0, and I'm going to leave the bonds VLAN as untagged and set the subnet to unconfigured. This is important because I'm using one logical interface for multiple purposes. Both east-west and north-south traffic will hang off the bond, but will be encapsulated in a VLAN. Now, in order for the setup to work, the bond must not have any layer 3 or IP configuration. I'll leave a link in the description of this video to an article on docs.openstack.org, which explains this in much better detail. So after that, I'll enable link monitoring for the bond and set some defaults so that if a link failure is detected, the bond swings the traffic over to the remaining active interface. Now I'll add the east-west VLAN to the bond, select the appropriate subnet, and then set the IP mode to auto-assign. Note that I'm not going to add the north-south VLAN here in MaaS. I'll configure this on the provider bridge inside of OpenStack once it's deployed. And then lastly, I'm going to add a tag to the machine, and I'll use this tag on the Juju CLI when I deploy the applications to the servers. Now, there's 2 ways that we can deploy with the Juju CLI. There's the easy way and there's the hard way. I don't want to do the whole deployment using the hard way, but I do want to do a couple of examples using the hard way to kind of give us some insights as to what's going on behind the scenes when deploying the easy way. Now, you may know that OpenStack consists of many components working together as one solution. The OpenStack-based bundle has at least 16 different components, all with their own configuration. Now, the bundle configures and deploys all of these things simultaneously. Now, when deploying at scale like this, it's kind of hard sometimes to kind of wrap your head around what's going on and kind of get the bigger picture. So what I'm going to do is that I'm going to break a couple of the concepts down, deploy some things manually, and this will give us really good insights as to what's going on behind the scenes when using the easy way. Now, I already have a Juju controller. It's highly available, and it's also got a couple of models that are holding some other things. So in this first example, let's use the Juju CLI to manually deploy Nova Compute straight from the Charm store, because it's kind of the foundation of the whole OpenStack ecosystem. So the first thing that we'll need is a Juju model to hold the configuration of our cloud. So I can go ahead and run a Juju add-model and the model name here I'm just going to call live demo. If we type Juju model-config, we can look at all the settings that we can set at the model level. Any applications deployed onto the model should inherit settings that are declared at the model level. And one of the configs that I want to set is the default space. So I can run a Juju model-config, default space equals admin network. And the reason that I'm doing this is so that any applications that I deploy will automatically be bound to the admin subnet, even if I forget to declare it. This is important because we need to ensure that the bond interface doesn't end up with any layer 3 or IP configuration as explained earlier. Now we can go ahead and run a Juju deploy charm store :nova-compute -- series is focal, and we're going to pass a constraint of tags equals demo. So that's going to send a request to MaaS for a machine matching the constraint. If MaaS finds one, it will begin deploying an OS to one of the nodes tagged with the demo tag. Now this will take a little while for the machine to boot and get an OS pushed to it, so I'm going to switch to a model that I prepared earlier. On this model, we can see that Nova Compute is already deployed, but you'll notice that the unit state is blocked, and that's because it's missing relations to a message queue provided by rabbitmq and imaging provided by Glance. So now we can deploy those required services so that we can get this unit out of the block state. So I can go ahead and run a Juju deploy charmstore rabbitmq-server, -- series is focal, and I'm going to deploy it to LXD and the unit number of an existing machine. So that's going to spin up an LXC container on the physical machine where Nova Compute is installed, but it will install rabbitmq into the LXC container. And what's nice about this is because it's an OS container, it behaves exactly like a machine. So you can SSH into it, it has its own file system, but the only application installed there will be rabbitmq. So it's really easy to troubleshoot and it's really clean. Once rabbitmq server reaches the ready state, we can now create a relation between Nova Compute and rabbitmq. So I can simply run a Juju relate nova-compute rabbitmq-server. What Juju will then do is configure the Nova Compute services and tie it into the message queue, which fulfills that missing relation message. So that's a little glimpse of what the hardware looks like. It's not rocket science, but as you can see, deploying 16 or more components this way will be a little bit time consuming. So let's get a little bit more efficient and use a bundle instead. Now I'm going to go through this next part really quickly, but don't worry, it's just an introduction to something that I'm going to explain in detail in a minute or so. So as mentioned, the OpenStack-based bundle can be obtained from the Juju Charmstore. And what it is a simple YAML file. And if we look at the contents, up at the top, we've got a series or OS definition, followed by some variables, then the number of machines that we'll be using, all the application definitions, and then right at the bottom, we've got all the relationships that we'll build between all of the apps. If we look at the definition of the apps, we've got the deployed application name, the charm source, the number of units for that charm, and the definitions for configurable options and a placement directive. So I've uploaded a copy of the YAML to the server where the Juju CLI is installed, and to deploy the bundle, I'll simply cd into the directory where the bundle is located and run a juju deploy /the bundle name. The controller will download all the charms, set all the configuration options, summon machines into existence from the underlying cloud, create all the relations, and place all of the application units on the relevant machine or container. After the bundle is deployed, it will take some time for the servers to be installed and then for the Juju controllers to configure everything, but we can monitor how everything is going with the Juju status command. And as you can see here, there's a lot happening on the model. So as awesome as all of this is, if any of the physical servers were to fail, the whole cloud would become unusable because multiple OpenStack services would go missing. So at the beginning of the video, I said I was going to deploy everything without a single point of failure. So let me show you a highly available Juju bundle that I've been developing over the last couple of months. I've uploaded a copy of the bundle to my GitHub, so feel free to download a copy and modify as needed, or just use it to follow along. The easiest way to see the differences between the standard bundle and the HA bundle is to compare them side by side. So go to the history on the repository and compare this commit side by side. The first change I made to the bundle was the data port mapping. The standard bundle uses the second network interface in the machine for north-south connectivity. As mentioned, I'll be using the bond I built for both east-west and north-south traffic. Next, I added an additional OSD device because the servers in my lab have 3 additional hard drives. So I can make my pool bigger by selecting both /dev/SDB and SDC. The number of physical machines goes from 3 to 6, and I've also added a series and constraint here so that the correct machines in MaaS get selected when deploying the bundle. The first noticeable thing I've done on the applications is to add a space binding. As mentioned, I'm going to be binding everything to the admin space, but this is the setting you would use to bind the applications in a multi-home setup. The number of Ceph OSDs gets bumped from 3 to 6 because I have 6 physical servers. And this is where it actually gets interesting. The first app that doesn't have native high availability is the Ceph Rados gateway. So I've added the HA cluster subordinate charm and deployed it as a named application, Ceph Rados gateway -HA cluster. And we do it this way because we'll be creating multiple clusters for every application that needs it. I've then deployed Ceph Rados Gateway itself, bumped the number of units to 3, and also created a relation between Ceph Rados Gateway HA cluster and Ceph Rados Gateway itself. Then I've also set the OpenStack admin internal and public host names and added a virtual IP. The virtual IP only comes into effect when the app is related to the HA cluster charm, and the virtual IP will get created as a cluster resource. If any one of the 3 units should fail, that virtual IP should move to surviving members of the cluster, and that service should still be available. Things to note here is that the host name is for the virtual IP and not the hosts themselves. In order for this to work, the host name must be resolvable before deploying. So in a previous step, I created an A record in MaaS so that the host name resolves to the virtual IP address of the cluster resource. Lastly, I've deployed all 3 units as LXC containers to machines 3, 4, and 5. Now, I've pretty much done this for every application that's not natively clustered. I've also added a couple of other things which make the deployment a little bit more relevant to my requirements. One of these things is the Glance Simple Stream Sync charm. It automatically downloads and syncs the latest Ubuntu images on a periodic basis into OpenStack so that you'll always have the most up-to-date Ubuntu images which you can use to build OpenStack instances with. Now, this isn't required for OpenStack to work, but it's just really convenient, and I think it should actually be included on the OpenStack base bundle. Something I found out along the way, when clustering Nova Cloud Controller, you will need a relation to memcached, otherwise it complains about missing relations, so that's something additional I've added, which is not included on the OpenStack base. And then there's a couple of application-specific options I've added, which are not set on the OpenStack base bundle, but make my life a little easier or more convenient. In the Nova Cloud Controller, I've added console access protocol to equal to SPICE, and this is so that I can see what's happening on the console of a machine, either as it boots or just to verify that it hasn't crashed or blue screened. On Nova Compute, I was experimenting with availability domains, so I've set the customize failure domain to true, but this is still work in progress. I haven't managed to get this working yet. But something that's really useful is setting the libvirt image backend to RBD. When you build an ephemeral instance in OpenStack, the default Nova Compute configuration writes that instance's boot drive to the local file system of the node it's spawned on. The problem with this is that you can't live migrate the instance to any other host. By setting this to RBD, it ensures that the ephemeral instance's disks are written into Ceph distributed storage, which is readable and accessible by all the hosts, which allows you to live migrate ephemeral instances. This is particularly important when you're building instances with Juju, as Juju will always build ephemeral instances. On the OpenStack dashboard, I've set the default theme to default because I personally prefer the native OpenStack look of Horizon as opposed to the Ubuntu themed one. I've also set the default create volume to no because when I delete instances, I typically want their data to be deleted too. I've enforced SSL so that I'm not submitting credentials over the network in clear text. I've also set the host name for the OpenStack dashboard to openstack.lab.dev0.home because that's what makes sense to me to type in the browser when I want to log into Horizon. Now, obviously, you can set this to any value you like. Obviously, that resolves to the dashboard's virtual IP as well. I've also set the password retrieve equals true because I do run some Windows instances inside of OpenStack. And this allows me to decrypt the randomly generated administrator password using the private key used to build the instance. And that's pretty much all the tips and secrets that I can share with you. Deploying the bundle is exactly the same as before, but once it's deployed, you'll now notice that the model is absolutely massive. So it will take a while for the model to settle, but it will get to the point where it seems like everything's stuck. But this is because the vault needs to be initialized. Once initialized, Vault will issue SSL certificates for all of the OpenStack services, and all OpenStack endpoints will be using HTTPS. So to initialize the Vault, I'll need the Vault client, so I can simply run a sudo snap install Vault. And as you can see here, I already have the Vault client installed. So then I'll need to export the vault_address shell variable to the IP address of the Vault leader unit. I can then initialize it by running a Vault operator init-keysheds equals 5-key threshold equals 3. Make sure to store the outputs returned by the command in a secure, safe place, as you won't be able to retrieve them again, and you will need these values to unseal Vault in the case of one of the Vault units getting rebooted or taking an outage. At this stage, Vault is initialized, but it's still sealed, so I will need to unseal it by running a Vault operator unseal with at least 3 different unseal keys. Once we verify that the Vault is unsealed, we can create a token to authorize the Vault charm. So we'll export the Vault_token variable to the initial root token obtained from the initialize command. We'll then create a new token, and after that run Juju run action --wait vault/leader authorize charm token equals the token that we just created. I'll then get Vault to generate a root CA certificate so that it can actually issue SSL certificates. After this, it'll take a couple of minutes for the model to settle as all the services get SSL certificates from Vault and switch from HTTP to HTTPS. And then once everything reaches the ready state, we can actually begin using OpenStack. We'll first need to get the Keystone admin password so that I can log into the OpenStack dashboard. So I can run a Juju run --unit keystone/0 leader get admin_password. I can then visit the OpenStack dashboard using the OS public hostname that I set on the model configuration. Once logged in, we can verify that all our hypervisors are registered with all the CPUs, memory, and storage. At first glance, the storage is a bit counterintuitive because the dashboard says that I have 24.5 terabytes of storage. But that's really because we're running Ceph and the storage pool is shared and visible to every compute node in the cluster. A big noticeable difference between the standard bundle and my customized bundle is on the API access under the project settings. Because I set the OS public hostname settings on each of the charms, all the OpenStack service endpoints now use FQDNs instead of IP addresses. Not only does this look really slick and professional, but all of the FQDNs resolve to the virtual IP addresses of each service cluster. So even if there's an outage or one of the service units is replaced, the endpoint addresses remain the same for cloud consumers. If we go down to images, we can see that the Glance Simple Stream Sync charm has already downloaded the latest Ubuntu images. So we'll be able to build Ubuntu instances right off the bat. Before we can do that though, if you recall at the beginning of the experiment, I said that I would be using the bond interface for both east-west and north-south traffic. To provide external connectivity for instances we'll be building inside of the cloud, we'll need to add that north-south or external interface here inside of OpenStack. So to do that, I can go to the networks on the admin section, create a new network and give it a descriptive name, select the project it belongs to, and in this case, it's a provider link, so I'll be associating the network to the admin project. The provider type I'll set to VLAN, and the physical networking is the logical name of the network interface defined in the Neutron API and OVN chassis charms. In my case, the segmentation ID is VLAN54, and I'll set the network to external and shared so that any other projects I create later on will be able to use IP addresses from VLAN54 as public IP addresses on their instances. On the next tab, I'll define the subnet names, address spaces, and gateway IP addresses associated to VLAN54. The IP address of the gateway is the IP address of the physical router or firewall, which provides access to the real-world networking. Lastly, I'll provide the name server addresses, and in this case, I'm just going to use my MaaS controller addresses to resolve DNS. Now, if we go to the network topology on the project, we can see the external public network. So I'll need to create a virtual project router and plug it into that external network. To verify that connectivity is working, I should be able to ping the software-defined router inside of OpenStack across the physical network in my lab. Once I've verified external connectivity works as expected, I can create the software-defined network that we'll attach our virtual machines to. So I can give it a descriptive name, the desired network address, and an optional gateway address. And then after this, I'll just provide my MaaS DNS servers as DNS resolvers again. If we look at the network topology now, we'll see the network that I just created is an island. So I'll attach a virtual interface from the software-defined router to the software-defined network that I just created. And now we have a functional network topology. Finally, I can build a cloud instance, so I can go to instances and launch a new instance. I'll call this one test, and I'll leave the boot source as image, and you'll notice that create volume is already set to no because we specified that in the charm options on the Juju bundle. For this instance, I'll use the Bionic image downloaded by Simple Streams, select the size or flavor of the machine, and then attach it to the inside network I just built. After that, I'll import my SSH public key so that I can log into the instance after it's built. And then lastly, launch the instance. So while that builds, if we go back and look at the network topology now, we can see that machine test is attached to the internal network, which is attached to the virtual router, which is attached to the HomeLab network. If we want to log into the newly built instance, we will need to attach a floating IP address to it because the internal network it's attached to is not reachable from the real world. So we can request a public IP address from the external HomeLab network and attach it to the instance. Now I can go ahead and SSH into our test instance, and here we can see that it's got an uptime of 1 minute. And if we look at the instance IP address, we can see it's from the 10.20.30 IP address range, which is from the internal software defined network, and not the 192.168.54 address associated to the HomeLab network, which I plugged into the SSH command. And that pretty much concludes deploying a highly available OpenStack with the Juju CLI exclusively. Massive amount of information shared on this one, so if you're still here at this point in the video, thanks for watching. If you like this video, give it a like. It kind of gives me a heads up on what people like on the channel and what they don't like on the channel. If you're new here and you like seeing geeky, nerdy videos like this one, please consider subscribing. But as for this video, that's all I have for you. I will see you guys in the next one. Peace.